Good afternoon, everyone, and welcome to today's session for Manure Mondays. This is our third one of the year. Today we have Jason Oliver from Cornell. So I have a few slides here, folks. So the Manure Monday series is supported by the On-Farm Climate Action Fund. So the OFCAF program supports BMP adoption across three practices here across Canada. So rotational grazing, nitrogen management, and cover cropping. And the goal of these is to support soil health, soil erosion, sequestering carbon, and efficient use of nitrogen. So, perfect case for doing these Manure Mondays. A little bit of housekeeping. My name is Georgia, and I'm the KTT and Agronomist Training Specialist here at Perennia. So if you have any questions, feel free to reach out. This webinar will be recorded, and then it will be on our Learning Hub on the On-Farm Climate Action Fund website. This webinar can go towards an off-CAF learning credit if you have a project under the program. We'll do Q&A at the end of Jason's presentation, and you can use the Q&A box. Okay, and through the Federation, just wanted to mention that there are a few sessions for transportation guidelines. There is one in Northeast Margaree on February 9th, so that's an evening session there, and then there's one in New Glasgow on the 19th of February. So two sessions coming up. If you have any questions on those, feel free to reach out and I can send you the registration. Okay, so for today, we have Jason from Cornell University down in Ithaca, New York. He is the Dairy Environmental Systems Engineer there, originally from Finger Lakes region. And he is on the Pro Dairy team there and joined that team in 2022. So he does research and extension in environmental stewardship in farming. So that includes the development of practical biotechnologies for the treatment of emissions, effluents, and greenhouse gases from livestock facilities. So the topic today, which I'm really excited about, is manure management and treatment implications on nutrients and greenhouse gas emissions. So Jason, I will stop sharing my screen, and thank you so much for being here. And I'll get you
Thank you.
started. You're welcome. Thank you.
Let's see.
I'm just going to shut off my audio, but I'm going to keep my video going.
Very good. You can hear me okay and see the slides good?
Yes, you are good.
All right, great. Yeah, thanks. Thank you for the introduction. And for those who have not been to upstate New York, to the Finger Lakes region, here's sort of an aerial image. It's a landscape that is predominantly agriculture, has some very big freshwater lakes, and is one of our big dairy producing regions of the state. So it's been great for me to kind of be from this region and then to be back here working professionally with all of our great farmers. Let's see, advance here. Here we go. Okay, so a little background on dairy in New York too, right? We're the fifth largest dairy producer in New York, and likely to kind of climb in rank as we've invested tremendously in processing in the last handful of years. We currently have just under 3,000 dairy farms and about 630,000 cows. That said, our average herd size is actually just over 200. So we've got about 600 very large farms, and then most of our farms are small and similar to some of the farms I've imagined in Nova Scotia. Our cows are producing about 11,000 liters of milk per year. Nova Scotia stats, and this is as much for me as for you folks. It looks like you have about 200 dairy farms in the state, about 21,000 cows, and your average herd size just over 100. So again, we have farms that are single cow, a lot of pasture-based herds, the most organic dairy farms in the United States. But then we also have some very large, 8,000 cow herds in the state as well. And my role with Pro Dairy is really to support all of the dairy farmers in New York State, really focused on manure management and that environmental stewardship. So anytime I really am thinking about emissions and thinking about nutrients, I'm really just thinking about efficiency. And I think this is something that dairy farms do really well, where they're always trying to find, kind of a more efficient, simpler way to do something. And so I think we can just apply that same sort of mindset to our management of our nutrients. And I think through that kind of approach, you can get some real benefits in greenhouse gas reductions and nitrogen stewardship. So today I'll talk kind of about the benefits and challenges of storage, which I really view as sort of our best BMP, our best management practice. I'll highlight what manure emissions really focus on methane and ammonia, methane being kind of the most important greenhouse gas from the manure side of things. I'll talk about some technologies that can fit at different scales of dairy production to kind of improve our efficiency, focused on separation, highlight a couple of advanced treatments, and then I'll kind of circle back to just some things we can do to just manage storages without really investing in big technology, and just kind of finish up with an innovative application strategy and some things I'm excited about. Um, so again, storage benefits and challenges, right? So step number one really is to efficiently control these nutrients so then we can manage them. Um, as I'm sure the folks on the call know, manure really is a mix of many things, right? And here's listing maybe some of the most common things that are part of manure, but maybe even not all, right? And depending on what the composition of your manure is, some of these components add different things, right? So bedding, wasted feed, actual feces from the cows are going to add solids, right? Other things are going to be adding nutrients. So the few I just listed, but also other things like barnyard runoff or feed center leachate, et cetera. Some things are going to be diluting our manure too, dumping waters, sprinklers for cow cooling. Maybe you're using some kind of flush water in your system, milking center wash water, right? Can all sort of dilute. But all of these things are really going to increase our volume, right? So as we really collect more manure to be better stewards of those nutrients and protect water quality, we tend to sort of have more and more material that we then need to manage. Um, One of the common storage strategies is liquid or slurry storage. Those can be pits, tanks, ponds, lagoons. I want to reiterate that those should be design systems. So there are sort of some pre-engineered storages that are still out there and working, but it's important and really required now for all new systems to go through a professional engineer. Um, they're relatively simple and relatively low maintenance structures, especially if they're designed well and really thoughtful with how they integrate with the farm. Um, and really, most farms have some kind of liquid form of nutrients they need to manage anyway, so it makes sense. Manure as excreted is really a slurry or pumpable material. Challenges, though, are as we build these storages, now we're also starting to capture rainwater. As we put this manure into these oxygen-free anaerobic environments, we also start to generate odor and we can start to generate emissions, methane and ammonia. Then there's some of the management challenges, right? Agitating these large pits and pumping them out. And then, as a engineer, I also do a lot of work with safety, right? So hydrogen sulfide gas is something else that can be emitted from these systems. It can be fatal at relatively low concentrations. We could also store manure as a solid, right? So depending on how your manure is collected and the amount of bedding, right? If you're a heavy bedded system, you might have more of a stackable manure. So these can be some kind of earth, gravel, or concrete pad. They could be open or covered. Um, Again, the benefits here is it really can help us facilitate the handling of that material. We can compost. But some of the challenges are we really need to think about leachate collection. We need these things sited well so they're accessible. Potentially some stormwater management that needs to get involved. Um, the other thing too with solid manure systems is we actually can lose a substantial amount of nitrogen through sort of the composting process and just the heating of that material in the form of ammonia, N2 or N2O gas, right? Um, There are also, setups where we're basically storing the manure underneath the cows. That could be a slatted floor barn in more arid climates that aren't really typical of Nova Scotia or New York. You might have lots, or composted bedded packs where you're actively managing a compost underneath cows to provide manure storage and bedding, right? These systems are all nice because the cow puts the manure in storage for us. They can be more challenging, however, because then we've got to manage, cows on top of our manure storage. Um, in the case of slatted floor barns, we start to have a confined space. So then again, there's sort of that safety risk. So with all of these storage systems, right, and really our housing in general, there's this kind of emissions piece to think about. So, again, storages were really intended to protect water quality, and there's some inadvertent air quality implications. And this is something that my team spends a lot of time actually trying to get out there and measure and monitor and understand how we can change management or implement technologies to reduce these emissions. Um, so again, thinking back about efficiency a little, right? I mean, these farm emissions can impact our climate and our environment, the health and safety of our animals and employees, right? Ammonia can actually is linked to bovine respiratory disease, right? And also impacting our relationship with our neighbors. Really, all of those things kind of come back to efficiency and economics, right? If we can keep our neighbors happy, our animals healthy, our employees healthy, our environment healthy, then we're going to be cranking right along more efficiently. So I don't really, again, separate these two things. So diving into what the emissions are a little more closely, right? When we're really thinking about cows and greenhouse gases, we tend to think about methane because it's really arguably sort of the more impactful greenhouse gas emission that comes off from cows. Globally, about 4% of the greenhouse gas footprint really is related to cattle production. Most of that really is enteric fermentation. So the cows are eating the carbon in the grass. They're going to belch out methane. That's going to go up into the atmosphere. After about 10 years or so, it's going to get converted back to CO2 and then get sucked in by the plants. And that's really part of this biogenic carbon cycle, right? It's sort of natural carbon cycling. Where our management becomes important, right, is when we start to put in these anaerobic manure storages, right? When we do that, we've taken manure that maybe used to set out on the grass, and now we've put it in an environment where it's actually going to increase the amount of methane that it puts off. Globally, the emissions from dairy production have actually gone up. This data is a little older, but um, gone up about 18% from 2005 to 2015. But over that same time period, we actually saw the milk intensity, the greenhouse gases attributed to basically the energy corrected milk produced, have gone down. And so again, efficiency is sort of helping us, right? We're producing a whole lot more milk, really, with fewer cows. And nationally, or excuse me, globally, I believe the average is around 2.5 kilograms of CO2 equivalents per that, fat and protein corrected milk. In the US since 1990, we've seen enteric emissions going up. But again, with efficiencies, we've seen a lot more milk production, and we tend to have a footprint that's around 1 kilogram of CO2e per kilogram of milk. But we've seen our manure emissions go up over 100%, right? And that's largely due, again, to this implementation of more storage to protect water quality. Um, in Nova Scotia, I looked up some data from your greenhouse gas emission tables, and it looks like your enteric has gone down a little bit, perhaps due to some, decrease in herd size, but your manure methane emissions have gone up, quite a bit, 500%. And again, I would guess that's largely due to the implementation of storage as a strategy to protect water quality. Um, I don't view that necessarily as a bad thing, right? We're protecting water quality. And now, because we have manure basically in a system that we can manage, we also have an opportunity to sort of manage these greenhouse gas emissions. The other emission that's, I think about a lot is ammonia. So a lactating cow can actually excrete about 70% of the nitrogen it eats. And most of that comes out in urine. Um, When that urine basically mixes with feces, it mixes with the enzymes that can then convert that to ammonium, so breaking down urea to ammonium. And that ammonium is very volatile and can be released as ammonia. Um, Ammonia is a criteria air pollutant, so it actually contributes to the formation of fine particulate matter and smog. It can be, a respiratory hazard breathed directly. We believe it's also sort of an indirect source of nitrous oxide because it tends to get deposited pretty regionally. And then that extra nitrogen that lands in the landscape or in waterways can either cause some nutrient pollution or can get sort of converted to N2O. Um, and I did mention this sort of relationship with bovine respiratory disease, right? I mean, this has been well documented in poultry too. Um, it's important to note that, at least in the United States, but this I think holds true globally, is about 80% of ammonia emissions are really from agriculture. And of that slice, about 25% are attributed to dairy production. So this is actually on the left, you see a map of 2017 of our kind of dairy cattle inventory. And on the right, our space agency, NASA, had done some satellite measurements of ammonia. And you can see pretty good overlap in some of our really heavily dairied, so like the Central Valley of California, and you see a big pulse of ammonia, the Snake River up here in Idaho. The Midwest is there's not only dairy cattle, but there's a lot of swine and poultry and just crop production in general. Um, you especially see a lot of this ammonia coming off in our more arid western states because of the sort of dry lot and dry stacking of manure versus the east, but you still see some synergies there. So anaerobic digestion is sort of one strategy we have to manage these emissions, right? And I think we hear a lot about this as sort of like, okay, this is a great solution. They're essentially fermenters that are optimized for methane generation. So you see kind of three different types we have in New York, sort of the covered lagoon, a plug flow digester in the middle where manure kind of goes in and flows in this big concrete tank, or a CST digester, which is a continuously stirred tank reactor. So it's a mixing vessel and heated. Um, they're really designed to promote methane generation, right? So let's put manure in, let's heat it up, let's ferment it, let's try and convert some of this organic matter into methane and then capture that methane and utilize it. We can utilize it either by running an engine to generate electricity, or what we're seeing more and more, and you see it sort of pictured in the plug flow digester, is a skid where we can then take that biogas and upgrade it to pipeline grade natural gas, and then use it in that in transportation systems or to heat homes or businesses. Um, if we model the impact of a digester, you can see sort of the baseline scenario here in gray, and this is using IPCC's modeling approach. And then we model sort of what the digester's impact is. There's almost a proportional reduction in methane based on, this organic matter reduction. So 35% of that organic matter got converted to methane in vessel, and so we imagine the manure after digester has 35% less methane that it can produce. Others have shown this too. This is some work out of Wisconsin. So they're looking kind of more holistically, not just at methane, but N2O as well. And you see the raw manure, and you see about that 30% reduction through a digester. The challenge with these systems, though, is they're super expensive, right? I mean, they have a lot of CapEx, OpEx, they can be millions of dollar projects. There are systems that scale down, right, to small farms. But again, they're expensive. And if there's not good energy markets, those systems tend to struggle to really become viable. The other thing that's important to note about a digester is while there's really no change in the total amount of nutrients, a digester does convert organic nitrogen to ammonium nitrogen, and thus it's sort of more prone to loss. And so, there's evidence, the team out of Wisconsin documented this, but you can actually have somewhat of an increase in ammonia emissions post-digester. And we've seen some of that in our measurements too, where manure post-digester can be substantially higher in the ammonia concentrations around storage. Um, so I want to talk next about manure separation. I think this is a technology that is sort of your best first step into advanced manure treatment. And there's a lot of benefits with separation. So essentially what you're doing, and this is a screw press separator I'm demonstrating here, which tends to be well suited for our scrape collected manure in the Northeast, where a slurry comes in. It gets through the screw press. The solids are kind of pushed out of the front, and in the process, the manure liquids are squeezed through a screen and drop out of the bottom. The solids become more stackable. They become a material we can export. Um, the 200 farms in New York that use screw presses largely use those solids as reclaimed animal bedding. And there's also some, nutrient partitioning that occurs. The liquids then are reduced in volume, so a little bit more capacity in your slurry storage. They're easier to pump and irrigate with, and they really are then in a better state for some advanced treatment that I'll touch on in a little bit here. So there are many approaches to separating, right? These are all different separators I've seen in our colder climates, right? You can have slope screens, simple picket dams, rotary screens, or the screw presses you see on the bottom that can either be set up with like conveyors or can just drop the solids down into a solid storage, right? Um, when we think about the scaling of this technology, really, you probably still have to have about 200 cows to, effectively have a separator. Um, Really, the main requirements are that you have some kind of reception pit so that manure needs to be collected somewhere where we can then utilize really three pieces of equipment to operate the separation process. You need a press that's actually doing the separation, and then you usually need some kind of mixer and a pump to circulate the manure around. In our colder climates, right? I mean, it's well below freezing out. We also need to have this be inside of some kind of building or facility. In the western states of the United States, they can actually just separate outdoors. We obviously would have frozen pipes. So there are successful, implemented systems at farms this small, and the system's paying for itself, right? And the farm's finding plenty of benefit in it. The economics do get better as you get bigger, and do get more challenging as you would, get smaller. Uh, So just to share some of the impacts on sort of nutrients, right? The separated solids, this is some average data from the 20 or so systems I've monitored over the last 4 years. You have separated solids can be sort of around 38, maybe 40% total solid. So a very dry, stackable product. And then the separated liquids tend to have a total solids content of less than 5. So they become a lot easier to pump and drag line application or whatever. Um, we see about 15% of the nitrogen captured in these systems. And we see about 10% of the P2O5 and the potash captured as well. So this is, a fraction of nutrients that now are in the solids. And so if you don't have enough, say, land base to responsibly recycle all your manure nutrients to, you might now have a form of solid manure with some nutrients that you could compost and find an export market for. And like I said, we see anywhere between 5 and up to 17% reduction in the total volume of manure with the solids coming out. So that can be a benefit in itself to many farms. We also believe that separation can reduce emissions. So I showed this graph before, right? On the left, you've got greenhouse gas, and on the right, you have ammonia. And there's a column that shows the stored emissions and the applied emissions for raw digester separated liquids, or excuse me, solid liquid separation, or the systems kind of running together. And then blue, green, yellow, and red all indicate sort of the emissions and what they're from. And so you can see there's actually a pretty substantial reduction in greenhouse gas emissions by separating because we're pulling all of this organic matter out. of the slurry before it sits anaerobically. And so now we're managing all that carbon aerobically again, right, as a compost. Um, we do think there's a drop in ammonia emissions, so just subtly, but some conservation of ammonia, nitrogen as well with that system, and substantially more reductions really in greenhouse gas than we believe just digesters can do. So um, these are some on-site measurements that we've been taking, right? So this is me with my Ghostbuster backpack on the right. It's a 30-pound gas analyzer that we walk around manure storages with, and then we can sort of estimate emissions flux. And this is just a snapshot of a few months, just to just give you make the point that um, things can be kind of variable, right? So the green bars are just untreated raw manure. So 4 farms that manage that way. The blue bars are farms that are managing separated separators, so they have separated manure liquids in storage. The orange farms have a digester and then separators, and then the purple farms actually are digesting food waste and manure and then separating. Um, so we don't always see a clean reduction with some of these treatments. That said, we're out there once a month taking a grab sample. Things are variable. So, CF5, one of the farms there, they why we have them as separated. They also will import unseparated manure into their storage. We don't always know what's in there at the time of measurement, things like that. Um, the October month would be more what we predict, right? Where we have some storages of raw that are a little higher in emissions, and then they typically drop down with treatment. So we talked about separation there and many of the benefits. There's also these opportunities to do some advanced treatment where we can sort of take that nutrient and separation a step further, right? These can be some pretty sophisticated systems, right? Even including reverse and forward osmosis, where we're really concentrating nutrients and maybe even dewatering manure, right? Um, so here is an example of the largest anaerobic digester facility in the United States. And this is actually it's in Wisconsin, and there are 11 dairies and I think over 55,000 cows worth of manure now. They're all being commingled and brought into one facility for processing. A couple of the farms are nearby and pump manure in, but all the others, it's basically trucks coming in and out. Um, at that scale, they're able to digest that manure, run a small suite of separators. They do some post-separation drying of the solids, and then that bedding goes back to the farms. The liquid that comes off the separators go first through basically an ultrafiltration step, and then forward and reverse osmosis, and they generate these, 3 different fractions where they have sort of off of the ultrafiltration, they have a nitrogen-rich liquid. Off of the forward osmosis system, they end up with a tea water that's enriched in phosphorus and potassium, but really low in nitrogen. And then off of the reverse osmosis system, they end up with potable water, essentially, that they are then able to discharge. So they have to reharden it and they have to temper it. But the water they discharge to the stream has lower quality than the water that they're generating from this process, right? This system is not something that's going to exist on a single farm. But what we have seen is some examples in Wisconsin where they've explored these sort of community systems where, working with municipalities, you're able to sort of scale up and then approach technologies that could then bring some real benefits to not only the farms, but the community, right? We can get our nutrients in a form that are easier to budget. Maybe an opportunity to get some of those nutrients to a crop farm that doesn't have livestock. And then, by separating out that water, we can really reduce the amount of material that needs to get managed on the landscape, or even have some opportunities to reuse that water on the farmsteads for cattle or something else. There are some systems that are a little bit more sort of suited for single farm application, and these DAF systems have been around for a while where they've kind of come out of wastewater treatment, and you use some sort of polymer to get the fine solids in the separated liquid to kind of clump together. And then in this case, they're using air bubbles and skimming to kind of pull that off. And then some presses to do some dewatering. This system was on a 2,000 cow farm, right? They're able to get about 85, 75 to 85% of their fine solids captured, which results in an effluent that has less than 2% total solids and the capturing of, about 80% of their phosphorus and 30% of the nitrogen, right? So then they have these things in a more concentrated form and these DAF solids that they can bring to far off fields or find some opportunities to maybe export from the farm. I will say that the system is expensive, right? The farm struggles a little bit with running this. These solids are not necessarily stackable at the moisture content they come off. And so I think we have some great farms that are willing to try things out, and we're learning from that, and we're improving this technology. And so I think in time we'll start to have solutions that really are better suited for you know farms and can scale down to smaller herds. This is a system that I think has some potential in that space, though we still don't have kind of an up and running system in our region that I have good data on. So this was some pilot scale work that we helped conduct. And so this is the Trident MD press. It's a much smaller footprint, right? It's on just a small little skid here. Um, we were able to get 90% of the fine solids out of the post separation captured. So our effluent had less than 1% solids, so very pumpable material. We were able to get 95% of the phosphorus and almost half of the nitrogen captured in these spongy solids you see on the far right. That material is very stackable and would be something you could pile up and handle with a loader quite easy. And you can see the actual, the nutrient content of those different processes here on the bottom, right? So you end up with that tea water. It's got about 8.5 pounds of nitrogen, 14 pounds of potassium, really no phosphorus. And then you have the MD solids, which are really a nutrient dense material, right? So constant innovation in this space, and I look forward to seeing, what kind of comes next here. Now, all that technology, again, I think you heard me say it over and over, really takes some scale. And there's some capital investment. You got to have the infrastructure. You have to have the electricity, right? So I didn't make that point maybe perfectly clear when I talked about separators, but there's some horsepower behind that equipment, and so you really need dedicated services for it. And so if your farm already is sort of like maxed out on electrical service, sometimes while the tools are affordable, bringing in additional electricity can become really expensive, right? So what can we do that's a little lower tech, potentially lower tech to kind of just manage the storage, right? And so I think of this in kind of some different buckets. We can do some just maintenance and management, um, potentially covering, though that can be pretty expensive too. And then a place that I'm spending a lot of time doing research right now is on additives and aeration. I see additives as something that can be really quite scalable. I think we just need some more concrete science behind some of that so we can build the right incentive programs to use those tools. On the management side, right? On the top, what you see is organic matter. So, this is Manure's organic matter, or volatile solids is how we would measure that. And on the bottom is the estimated methane produced. And again, this is all done using the Andrew van der Zag's IPCC MCF calculator from the IPCC methodology. So as we slowly fill our manure storage over a 12-month period, we see this generation of methane, and it tends to peak in those hot summer months, and then goes back down. And as that methane's being generated, there's this conversion of organic matter to methane, and so you see at the same kind of filling rate. And this is a scenario for 1,000 cow herd, but you could remove a zero and say it's a 100 cow herd. This is what this would look like with just no emptying. Now, if we emptied the manure pit in April and October, which is maybe what many farms do, right? We kind of get it out there in the spring, we plant our crops, we harvest our crops and get manure out there again. Under that scenario, while we are reducing the amount of organic matter in storage, we're not really knocking it down a ton in the summer. And so we still have this generation of methane that you see on the bottom. Now, if we can actually keep our manure storages empty in the summer, we can have some substantial reductions on methane, right? So then it's sort of like, well, how do we do that? Um, we're using storage to protect water quality, but how do we budget those manure nutrients in the summer to keep emissions low, right? One thing is something I think a lot of you are probably already doing is pasture-based management, right? And maybe even daily spreading of manure. Um, while that can be a good strategy to reduce emissions, if we're daily spreading, sometimes that can get kind of high risk from a water quality standpoint, right? We're spreading those nutrients regardless of soil and forecast. Um, we also typically see, reduced greenhouse gas emissions per acre of land, but generally a lot higher greenhouse gas emissions per unit of milk. And then, this kind of strategy of manure management just becomes less and less feasible as herds get bigger. And they don't have to be that big for this to become real challenging. Um, a colleague of mine, Augustin, did some work, and this is published in the Journal of Dairy Science, where he looked at a lot of different types of pasture-based herds in New York and looked at their greenhouse gas emissions footprint. So this is on intensity basis, so corrected for fat and protein corrected milk. This dash line again is sort of where our state average is, and you can see a lot of these farms, their footprint is actually higher. And in some cases, especially if it was we have some herds that are certified grass-fed, which has a lot higher threshold for basically days on pasture and what they're being fed. They can have a much higher greenhouse gas intensity, almost double what our sort of state is. Um, the other thing that's just, a total struggle with the system, and, when I look out the window today, we're not really growing grass. And so, while this is really kind of can be a good seasonal approach, we still have this kind of winter management. Now, if we do a good job with pasture-based management and we're keeping our manure storages empty all summer long, right? And then we're utilizing those systems in the winter and wet months, that could be a real win-win situation, right? Um, we see a bunch of farms in New York that are really gaining interest in covering manure storages. So this is an earthen manure storage here. And the same kind of material you might use that's a synthetic liner, it's HDPE, can actually be welded together and fixed on as a cover. Um, we do recommend currently that there's some kind of upstream separation before this technology is used because you can't really get in and agitate underneath, but we are seeing some pretty slick designs that might help us basically cover storages without separation. Um, Once we cover that, then we have an opportunity to catch all of the emissions that come off and run them through a flare where that methane can be converted back to CO2. And the data we have shows that we get about 80 to 90% reduction in that methane and also just substantial reductions in odor, right? We're basically taking those gases that come off and we're burning them through a flare, so we're treating them. So the graph you see on the bottom here in the black is showing gas production and red is showing when the flare is kind of capturing that gas. So in those shoulder months, those cooler months, we can sometimes struggle to maintain a flare. But when gas production really starts to ramp up in those warm summer months, the flares can chug right along and mitigate them. I like covers because they give us this sort of greenhouse gas benefit, but I think from the farmer perspective, they also give us some really important co-benefits, right? So the main is that we exclude water. So I looked up your average rainfall, right? I think I'm going to say inches here because I don't always think in metric, but you're around 50, 55 inches of rain a year. It's a little more than we get, but not a ton. And so if you had a 40 meter diameter circular storage, that would be about 1.8 million liters of rainwater that would be saved, right? And so by doing that, now we have basically rainwater that we can manage as clean water, right? And we don't have to manage it as manure and manure nutrients. That can be a huge savings cost in land application and just generally less manure to manage. And some farms, they're able to take this water off the top and do some stuff with it too, right? They might be reusing it around the farm. We also have some data, not a lot yet, that shows covers can really conserve nitrogen. And more so than just the savings in dilution, we actually think the pressure of the cover keeps that gas kind of in the manure so that the manure that comes off is just sort of enriched in nitrogen. That can be a benefit. We typically are seeing farms apply manure to meet a phosphorus rate and then have to bring in some additional nitrogen fertilizer. So if we can retain more nitrogen with our manure, we might be able to get those things in balance and not bring any fossil-based fertilizers. But again, that's where you have to have, work with your nutrient management planners and kind of make sure this all budgets out. So I mentioned additives, and this is a graph again from the Andrew Vanderzag team up in Ontario that looks at some different additives and their impact on, in this case, cumulative methane. Right. So the gray is the control. So this would just be manure runs through, and then he has some different treatments in here. He has gypsum, calcium sulfate. He has acid, sulfur, or excuse me, sulfuric acid, H2SO4, and then another acid that's phosphoric acid. So what we're seeing here is A are sort of low dose and B are high dose. And the main takeaway is that gypsum alone, so because of we believe the sulfur in the gypsum can actually knock down cumulative methane emissions pretty substantially. But then if you pair that with an acid that is not only adding sulfur, but is also dropping pH, we can get a much more substantial reduction in emissions. The low pH is doing a few things, but the main thing it's doing is it's impairing the microorganisms that generate methane. And so it's sort of a one-two punch of sulfur, which is selecting for bacteria that compete with the methane generators, and then adding that acid that is directly impairing them. So we similarly have been doing work in this space. This is a study we did a couple of years ago where we used actually a nitric acid, and we dropped pH just, a point basically, right, from 6.7 to 5.4. And the methane concentrations that we measured throughout a summer coming out in the control could get as high as 800 or 760 parts per million. And with the treatment system, we never got above 3 parts per million methane. And then similarly with ammonia, we saw a big reduction, and that is really driven by pH. So when you get pH down below 6, instead of having ammonia, you have that nitrogen in the form of ammonium, which stays soluble and stays with the manure. Um, so there could be some real significant benefits to dropping pH alone. There are countries that are already starting to do this. I know in Germany they do they add some acid, especially for manure that they're spreading on top of hay ground. They have a lot of permanent sod hay, and they have really strict ammonia regulations. And so they're using this as a way to keep that nitrogen with the manure and try and get it into that grass instead of into the air. We're also really looking at the ability to acidify separated manure solids as bedding and other beddings for its ability to reduce ammonia, but also perhaps mastitis risk. So this is one of my students taking some in-barn measurements with a chamber. And what you see on the graph is a whole bunch of just different manure samples. And again, if we can get below 6, we can conserve ammonia. And if we can get down below 3, we can probably kill pathogens. And so can we take these separated solids and maybe even just dosing at 4% with some of these dry acid materials, we can get almost all the manures down below a threshold where we're not losing as much ammonia, right? And maybe even getting some of them down where we're having some pathogen kill and really improving the quality of that material as cattle bedding. So before, when I showed you kind of a bunch of the farm data, looking at, with and without separation, et cetera, this is a different look at some of that data where we're comparing each monthly measurement, which is in green, to the predicted emission, which is in gray. And this would be all for methane. And then CF1, 2, 3, and 4 are different farms. And the main thing I just want to point out here is this farm CF3. So this farm routinely had very little methane production, even in the hot summer months, way below modeled emissions. And as we dug in a little bit deeper, we found that this farm actually uses quite a bit of gypsum and actually uses another biological additive too. And we believe that these manure additives are the reason that this farm's manure storage doesn't generate as much methane, right? So we've now started to try and replicate that system in the lab to see if we could verify that. One way we've done that is we've developed these buckets with a small chamber that snaps on the top. And so we essentially have created these really small manure storages, and then we have the ability to measure emissions flux from them. And the graph is a little messy. We're early in this process with my student Joelle, but what we do see is for some dosages of gypsum and the biological, we can get 50% or more reductions in methane. And where we're going next is looking at some of the synergies of these. So if both products are together, can we really nail emissions and knock them down substantially? Um, so we also are able to measure ammonia and nitrogen with some of our setups. And so on the left, you can see Joel measuring some of the buckets. And in this case, we're looking at cumulative ammonia over time. And you can see we can also, with some of these products, knock ammonia emissions down. We've also more recently developed these manure mesocosms. There's 7,500 liter manure storages with controlled ventilated headspace, where we're starting to do some whole season trials looking at different additives and their impact on emissions. And with this project, we are starting, at least with this first trial, we saw some gypsum and gypsum plus this biological together could have, 25% reduction in ammonia emissions. I do want to just say we shouldn't get crazy excited about gypsum just yet. I think we need to figure out the dosing, and we also have to really be mindful of hydrogen sulfide risk, right? So anytime we're adding more sulfur to manure, we also run the risk of generating more hydrogen sulfide gas, which can be, quite poisonous and is really, it's not like it's going to, be harmful to the neighbors, but it's going to be harmful to the farm folks who are managing the manure and agitating those pits. So we really want to be mindful that we're not trying to like solve one thing and creating an intended consequence here. Um, the other technology that we're starting to see more interest in is aeration. So this is the dairy power system. This is really developed in Ireland and was intended to be a manure agitation system. And so it is basically a small blower with a bunch of valving. And so it has a whole bunch of different zones in the pit. And then so for just, 5 or 10 horse blower, you can slowly aerate all different areas of the manure storage. These, these bubbles that come off are big, as that just showed, right? It's intended really to mix the manure and keep it agitated, keep it pumpable. But we are introducing quite a bit of oxygen. And so we're actually changing the dynamics of our storage now. Instead of it being a big fermenter, it now has enough oxygen that we can, we're starting to see maybe an over 50% reduction in ammonia, or excuse me, in methane. We do see a reduction in odor and hydrogen sulfide risk as well, right? So, this starts to get me thinking, okay, if we have an additive that can really knock emissions down, maybe paired with something like an aeration system, this could all work well. Um, the other thing, and I guess it's not showing up here, we have a project right now where we have this system set up in one storage, and right next to it is another storage without the aeration system. And we're really trying to understand what are the nitrogen emissions and impacts on the form of nitrogen. Do we see a reduction in ammonia or an increase? Some of that data isn't well resolved. And so really trying to think whole system on how these things could work. Um, so just in wrapping up and make sure we have a few minutes for questions, I just want to highlight one innovative manure application technology we're also interested in. Um, and it's this thing called the 360 manure rain. So what this is it's a boom system that is on a reel and is an autonomously operated applicator. And so essentially it's integrated with some floating pump on the manure storage, and it has pre-programmed routes, and it can go out and basically apply low rate manure application on a growing crop, right? So here you can see drop tubes set up where this system can actually apply on corn, basically all the way up through tasseling. What gets us really excited about this is it's okay, we're finally maybe getting to the point where we can get nutrients out to the growing crop rather than kind of front loading it before the corn is up and growing. And then it also is enabling us maybe to keep our storage volumes drawn down, so we reduce that kind of nutrient loss and impact on greenhouse gas emissions. Um, these these technologies is pretty new. We just got the first two in New York last summer, and so still a lot to be learned about how this can improve yield, or what kind of the full system benefits are. There's certainly some kinks to get worked out. Fields need to be thought out, and how this thing gets set up. But I do think there's a real opportunity, and I think we're going to see more and more of these kind of unique, maybe autonomous pieces of equipment out there that are going to help with management. So just in wrapping up, right, there's a whole bunch of workable solutions out there. They really range in from simple to most complex, and then they range in their ability to kind of reduce emissions, right? So, and then depending on what emission we're looking at, these things might shift around in their performance and ability. So I try to keep my eyes focused on these things that are less complex, maybe more scalable, and are more reliable in their potential. But I think we're all still learning together, and totally interested to hear from farms in your region, and what you guys are thinking about too, and Gales. So with that, I'll just put up a quick thank you really to my team, right? None of this is possible without, a good technician and good graduate students, and really an exceptional undergrad. She's been kicking some butt lately too. And I'm happy to share my contact info, or you can get it at a later date. So
Awesome. That was great, Jason. Thank you. Great information. We have one question here. We have naturally, I knew this was coming up. We have naturally acidic soils here in Nova Scotia. Have you seen impacts on overall soil pH by acidifying and then applying manure?
yeah, so that's a great question, right? So we are just starting to do some of the more agronomy work in our region to get at that. But in countries in Europe that have been doing this, they haven't seen any real negative consequences. Um, you folks are probably putting some lime down, I imagine, anyways, or something to mitigate. So there's not when you look at the amount of manure you're putting out, it's really not so much material that you're going to be like changing the soil pH drastically, right? And we haven't seen manure application do a lot of that here. So my friends who are agronomists tell me it's not something we need to worry a lot about, but we are basically setting up some trials, hopefully this summer, where we're going to be putting out some acidified manure next to unacidified, and starting to set up some of those long-term trials so we can more, um, answer that question with some more certainty. Yeah.
Okay, wonderful. Awesome. We have another one here. We use powdered lime in dairy manure bedding that has brought up field pH dramatically over the last 5 years. Would this higher pH potentially be raising our methane emissions in this case?
So you're not going to get methane from the soils as much, right? So greenhouse gas from the soils are really nitrous oxide emissions. And I don't know if anyone's got really great data on that, because it's so hard to measure nitrous oxide. It's very fleeting, right? It's like very much a microbial process, and can be a consequence of not nutrients, but of like rain and soil water conditions. Um, we haven't seen differences in manure storages where the farms are using like a hydrated lime on the solids versus not. But those are some of the things, as we get a bigger data set, we're really trying to dig into, really looking at like what the storage system itself is putting off from a methane perspective.
Mhm.
The acidified product we're looking at could maybe replace this lime too, right? And so if you're getting some soil buffering benefit from adding that material. Maybe that doesn't work for you, right? But we've got to kind of explore solutions for everybody and see what fits.
Okay. So with the and then he's referring to the powdered lime in the bedding. So that would
Yep.
be the same. Okay. Okay.
Yeah. Yeah. So
Okay.
we have farms that are, up to 6% use, hydrated quicklime in
Yeah.
bedding. Some are putting a bunch on the top, some are mixing it in. So we have a lot of farms doing that too. I mean, it acts as sort of an astringent, and it's helping knock down some of that, mastitis risk, right? So yeah, I mean, and some farms are getting that soil, you're adding a bunch of lime right to the manure there instead of, adding it in the field, right?
Yeah.
Um,
Okay. I have a question too. In terms of different types of bedding, what have you found for manure technologies? Like what works best for different types of bedding, I guess, with separation and digestion, and I'm sure there's a lot of
yeah.
different cases.
Well, the one thing that works the worst is sand.
Yeah.
So we have a lot of farms that like to use sand because it's a pretty low maintenance bedding, right? I mean, I can throw sand under a cow, I have a pretty predictable outcome. She's going to be comfortable, and I don't have to really manage the stalls. But then everybody on the crop team has to deal with sand and everything, right? And wearing out pumps and equipment.
Mhm.
Um, we have farms that use shavings and use shavings successfully, but we do have challenges with consistent quality and green shavings and sawdust can sometimes have their own mastitis risk associated. We also see any of the wood shavings can be really hard on cows' hocks. I think the fines kind of blow out and you end up with these little pointy pieces of wood in there. There are farms using recycled paper sludge, so material from mills that again can have really inconsistent quality. And then the farms that are separating, I would say in New York, we probably have 200 farms using separation equipment. They're all basically using their separated solids as bedding. Um, we have a current project to really dive in and figure out, what the secret sauce is there because some farms are having great success and some are struggling, right, with mastitis and milk quality perspective. We can't always blame milk quality and mastitis on bedding, but it is one piece of the puzzle, right? So we have some farms that have gone to a light dusting of bedding every milking and have good success. We have farms that are using it once a week in deep beds and are having really good success, right? So we're really trying to figure out what, is there a specific moisture content? Like, what is it that is really making it tick. I will say, like all the farms that are having success with beddings are actively managing it, right? I think that's one key takeaway where sand is maybe more forgiving. I think when we're going to be using these organic bedding materials, we really got to be paying attention. We've got to be grooming those stalls well. Our stalls need to be properly sized for the size of our animals, et cetera. So
Mhm. And can we talk a bit more about the economics of the separation and some of those, because you said it was about 200 to 300 head where it's working on those
sure.
farms.
Yeah.
Do you have any case? I'm just thinking about our producers here. Do you have any cases where there is those smaller farms and maybe they're reducing their fertilizer inputs and reducing their bedding inputs? Um,
Yeah. So I mean, it's betting savings is usually the main thing that
yeah.
pays itself off, right? Um, and then ease of manure handling. So some farms are paying a third party to haul manure for them, and their rates are actually better if they're doing some separation and stuff because it's easier to handle manure. I know many of our custom haulers will actually charge a premium for sand laden manure.
Mm,
So those things start to add up. A system that would fit on a 700 cow farm, you're probably talking like 70K for the separators and stuff. But again, that's all really going to depend on the farm itself and their electrical infrastructure and do they already have a reception pit that can be used, right?
mm,
Or are they needing to pour like an additional concrete pit to set that system up?
gotcha.
Um, there are, we've talked a lot about, systems that maybe could be shared between farms, but it really takes there needs to be some like government and cost share involvement to make stuff like that work. Because the farms would still have to have some kind of reception pit and then maybe a system that moved around. I know Cuff Farm Services in Central New York that services a lot of the whole Northeast has also thought about kind of like building a system inside of a small half container where a farm could maybe just pour a few concrete walls and they could just, the system is quite, modular and could be dropped in. But yeah, it can be very farm dependent.
Okay.
Um, I don't know
Yeah.
if that answers your question well enough, but yeah.
That's okay. Yeah, I think we have some smaller, 100 head cat operations where,
hmm
looking for that next step
hmm
but maybe the technology's not there yet or the
It's
economics
it's
aren't there
getting
yet.
it's getting close, right? And I think the other thing that's really changed is the presses are producing a much more consistent product now.
Okay.
And so that is increasing the material's utility as bedding, right? And there's new controls that are affecting really increasing longevity of the screens and the augers on the inside. And so they're really reducing some of the operating and maintenance cost.
Okay.
And so I think we're getting there for sure, right?
Okay,
Yeah.
that's good. Okay, last question before we sign off, unless anyone else from the audience has one. Mine was just around the why. So, what's driving these technologies? Is that the industry itself, environmental regulations, or is it efficiency on farm, or maybe it's a big mix of all of it?
Yeah, I mean, it really can be a mix, right? I mean, so when I think about why digesters were first used in New York, it was really odor mitigation, right? It was
Mhm.
like our farms were like, hey, I want to find a way to have a less stinky farm and be a better neighbor. And then they started to see these secondary benefits of energy generation, right? I think with separation, it's, the same thing where, okay, we're improving our manure handling. We're also starting to get these greenhouse gas reductions. We do have some, groups that have been able to sort of start to valorize some of those greenhouse gas reductions and say, hey, our milk we can verify that it's lower, footprint and we can sell it for more, right? So I think, really all the above, where it's, um, our license to farm is going to continue to be challenged, I think, as we have more and more people living in proximity to farms and with less understanding of farm systems. And so, these technologies, I think, are helping farms kind of like, stay competitive in some ways.
Yep. Yep. That makes sense. Well, Jason, it's been an hour now. Thank you so much for your time and information today. We really appreciate it. We have your coworker, colleague Kristen, coming on next week
Yep.
or next month.
Yep.
Yes,
Kirsten Workman. Yep.
Kirsten. Yeah,
Yep.
looking forward to that. So
Yeah.
thank you again. And if people have questions, do you mind if I communicate
Fine.
between you guys or
Happy to answer questions.
wonderful? Okay. Well, you take care. Enjoy your week, and I hope everyone stays warm out there.
Yeah. You too.
Okay. Bye now.
See you.